Vasco, I met you a bit by chance. I'm introducing you just real quick, and then you'll be talking. So I met you a little bit by chance at a dinner. You were at a plasma physics conference, talking about how to recycle the CO2 from the Earth atmosphere. And then it turns out that you and your team had realized that the Mars atmosphere actually has the perfect environment for doing what it is you're doing to CO2, converting it to O2 using cold plasmas. And so today we will hear about this sort of tech transfer to ISRU. And I'd like also to thank you for agreeing on such short notice to do the talk. This was it was great. We had a cancellation and you stepped in, so I really appreciate that. And we're happy to have you today.
Oh, thank you very much.
Sure.
It's also a pleasure for me, and it's really funny, in fact, the way this connection appears, a bit out of context, but it's nice anyway. So maybe for the benefit of the presentation, I will minimize this screen.
Why don't you go full screen with your PDF? Can you go full screen?
Full screen. The PDF is already full screen. So I think I will just do something like this. Oh, is it fine?
Okay, sure.
Okay, good. So if there is some issue, just warn me. And if I arrive close to the time, warn me as well, please.
Okay.
Maybe you could minimize the outline on the side of the PDF.
Like if you close your bookmarks?
They are closed in my screen.
Okay.
Oh, okay. All right.
Okay, let me just try to go back then, because in my screen I put the PDF on full screen.
Are we seeing your screen?
Is there a delay
or is it your screen?
No, we're viewing his screen. There might be, depending on what window he selected, it might not have switched over when he did the screen sharing.
Okay.
Okay, well, this is fine. We can move forward.
Yes? Okay.
Yes.
Yeah, that's, as Julie was saying, I will share a bit the work we have done on the CO2 plasmas, also focusing a bit on this oxygen production on Mars, of course, because it's interest here. Let me just start by naming our team in Lisbon. So Paulina Globina, Tiago Silva, Loan Terraz, and Maria Grofulovic. And we have been working together with the colleagues at the Netherlands. I will mention here Ana Silva, and in France, Ana Sofia Moreira Candas and Olivier Gaitela. And there are, of course, many other people involved, but for what I will present today, these are the major contributors. So Mars, I think I don't need really to put a motivation on this. So it's on the agenda for many space agencies and okay, SpaceX as well. So NASA is sending a rover, SpaceX announces landing. ESA is also planning missions to Mars, Japanese space agency as well. And here the interest is related to this production of fuel and breathable gas using local resources. And I guess also everybody knows, but so Mars is essentially a CO2 atmosphere. 95–96% is CO2, and then about 2% of argon and 2% of nitrogen as the second major constituents. Temperature is lower than on Earth, about 210 Kelvin on average, and pressure is also lower than on Earth, so about 4.5.
Vasco, excuse me, I have to interrupt you. Have you been switching slides?
I have just one slide in front of me, which is with this Mars. You don't see it.
Okay, no, we don't see you switching slides.
Okay.
Can you like close up your PDF and, oh, now we see it. Okay.
Yeah, because I exit this full screen mode. So let me do the, as you say, so I will close the navigation tab.
Okay.
Yes.
Okay.
Let me do it in artisanal way. Yeah. Okay, so it's not really a full screen, but it will work. So I was showing this slide.
Okay. It works. Thanks.
Okay. So, of course, traveling to Mars is yeah, quite an adventure. It's very far away, depending on the position of the planets in the orbit, something between 55 and 400 million kilometers. If we want to use the most efficient transfer opportunity every 2 years to launch the mission, so it's represented here on this figure. So of course we take the position of Earth and we optimize the orbit so that we arrive at the maximum when we reach Mars. So we have this relatively narrow window to launch. It's a quite long trip, 180 days more or less, crossing all sorts of radiation and so on. And then if we want to land and return, we need to wait for about 1 year to have a similar opportunity on a similar orbit to return. So it's really a big adventure, many difficulties. Of course, all logistics is extremely complex. Basic things like water, air, fuel, food, everything has to be planned. And still, I don't know if it is realistic or just as a motivation to push forward, but what is common said is that by the end of 30s, maybe humans will land or arrive on Mars. So it's of course that everything that we can produce locally instead of carrying is extremely important. So any gram in a spaceship counts. So in this major challenge of going to Mars, we are focusing on a small part, which is initially was this idea of producing oxygen, so how to breathe on Mars. So create a breathable environment through oxygen production and again using the local resources. So I guess that we understand that the resource we are looking at is the oxygen that is on the CO2 from the atmosphere. And what I will discuss a bit in the next few minutes is then how can we decompose CO2 to get this oxygen, and why we think that plasmas are interesting to do this decomposition of the CO2. And for this I will then support now first these claims with our research on the CO2 conversion on Earth, and then in the end of the lecture I will try to show the first results that we have for Mars and to make this parallel of what is similar and what is different on Mars. So decomposing CO2 on Earth has also a very obvious motivation. We know that we are burning more and more fossil fuels, increasing the CO2 emissions with impact on global warming and climate change. And we also know that renewable energy should be a part of the solution. But there is a famous and a knowledge problem between the mismatch of supply and demand of energy. So when and where it is easy to produce energy from sun or wind, for instance, it's not where and when we need to consume it. So a major step is how to use this renewable energy in a way that we can then store the production of energy. I don't believe in any magic solution for this problem. But so it should probably be a series of many different variants on how to address this problem. But the partial solution is the production of CO2 neutral fuels or solar fuels or synthetic fuels, whatever word you want to make. And it is the idea of using CO2 as a raw material. So CO2 would not be a problem, or a big problem, because we are taking it as the raw material to produce our fuels. So we should go somewhere in the step to the production of syngas, so CO plus hydrogen. And if we do this, well-established chemistry allows us to produce hydrocarbons and liquid fuels. So let me use the word gasoline. So we can, if we manage to do this, we can, let's say, keep using the same fuels that we use now, but they will not come from fossil resources, but from renewable energy and from the air, so to say, from the CO2 that is there. This, of course, has many advantages, keeping the infrastructure that already exists for distribution of the energy, for transportation. All the engines could still run. And it's probably the best way to store energy from the point of energy density. So we can keep a barrel of gasoline for a long time, and the density of energy per kilo or per liter is very, very, very high. I should, in fact, put here a figure with this to compare with batteries and other things, but it's orders of magnitude the difference. So a critical step here is the decomposition of CO2. So one of the first steps is to break the CO2 molecule, which is extremely difficult because thermodynamics is playing against us. CO2 is very, very stable, so we need a lot of energy to decompose the molecule. So the picture is something like the cycle for water that we learn in elementary school, but we would make a cycle for CO2. So we would take CO2, let's say, from the air. So it's another important step. Then, using renewable energy, we would convert the CO2 and decompose it into CO plus oxygen. Then there is another parallel step that I will overlook at this moment because we are focusing on this line. And so I use a cooking phrase, that then we add water to our process and we produce our fuels. And then we can burn them and we close the cycle. So this would be a CO2 neutral cycle for the production and consumption of fuel. It's not reducing the amount of CO2 that already exists, but it will not increase the amount of CO2. So why then to use CO2 plasma, to decompose CO2? So this critical step of decomposing the molecule, why plasmas can be interesting. So plasmas are ionized gases. We have free electrons. They are light, so they can be easily accelerated by electric fields. In turn, the ions are much heavier and remain cold, and the neutrals are not accelerated by electric fields, so they also remain cold. And so we have a very pictorial image of what's happening. So a fast electron arrives, hits the CO2 molecule and can break it into CO plus O. So this is the first cartoon-like image of what plasma can do to the CO2 molecule. However, these direct collisions are not very efficient because we have to go through the excitation of a very high electronically excited state. So we need to give much more energy than the dissociation energy to follow this path. But it is relatively easy for typical plasma operating conditions or discharge operating conditions to make the molecule vibrate. So electron collides with the molecule, and instead of dissociating it immediately, it just puts the molecule to vibrate. And then there is something for us to remember and have immediately an image of what's going on, that I say that we can then try to make the molecule sing. So it's not really a resonance process as it is shown in these pictures, but if the molecules are already vibrating, in some conditions, when they collide, they can increase their amplitude of vibration. And if they keep increasing the amplitude of vibration, they finally can dissociate, or at least they can be easier to dissociate because they are already vibrating a lot. So how does this song of the molecules, how this transfer of energy to higher amplitude of vibration takes place? It's what we call VV, from vibration up pumping. And I will try to give an idea of what it is here first, and then show an example, which is for me one of the most beautiful images on plasma physics that I will also explain, which is a manifestation of this phenomenon in nitrogen. So the main thing is that the potential is anharmonic. So there is a very schematic representation here. So the distance between the two atoms of a molecule and the energy spacing between two consecutive vibration levels is decreasing as we increase vibration quantum number. So if it would be an harmonic oscillator, energy spacing would always be the same, but it's not an harmonic oscillator, and then this energy spacing is decreasing. So what happens is that when a molecule in a certain quantum number collides with another vibrating molecule at a different quantum number, these transitions, if in this picture the quantum numbers V and W are relatively close, I always say that nature likes resonance. So it's the levels are close, these transitions are nearly resonant, and so they are not very difficult to take place. But it's more likely that the molecule in the lower level will de-excite and the molecule in the higher level will excite than the opposite, because this is the exothermic sense of the reaction. And so this is the idea, the main idea that is interesting to keep in mind. So if two vibrationally excited molecules collide, they transfer energy from one to the other in a relatively easy way, but it's more favorable that the molecule that is vibrating less becomes vibrating even less, and the molecule that is vibrating more becomes vibrating even more. So this manifestation of this mechanism is beautiful, seen on the picture here. It's a nitrogen discharge with a gas flow coming from the left. So here we see the end of the discharge. So we see this bright emission of light. So our plasma is fully excited. And from this point to the right, we are downstream. So we are in an afterglow. We do not have anymore an electric field. So everything is recombining and is decaying. So we are evolving towards thermodynamic equilibrium. And what we see is that, okay, the light starts to disappear, to fade, and to eventually we don't see anything more. So this is what we would expect. We don't have any external excitation. Our system is just relaxing and dying out and thermalizing at room temperature. But further downstream the discharge, we see a re-emission of light, which is quite impressive and quite significant. And this is the surprise here. So remember, there is no external force. This is just relaxation. So where does this energy come from and what is going on? I usually joke with my colleagues from high energy physics saying, I know what dark energy is. So dark energy is what happens here in the middle. So somehow this energy is transported and is released a bit later. And what happens is, as in this dark zone, we are pumping this vibration energy. So we are having these collisions between vibrationally excited molecules and exciting more and more the vibrational states. Until after a while, we have a new chemistry that takes over because we have new particles that were not present before. So the right-hand side figure shows a vibrational distribution function, so population of vibrationally excited states as a function of vibration quantum number in the afterglow, and here is time in a logarithmic scale. So here it's 10 to minus 7 seconds, which is basically the same distribution that we have in the end of the discharge, so here. And you see that at quantum number 35, 40, we have no molecules. As we move on so we are number 35 and 40 that were not present before, and they will start the new chemistry that you see here on the light that appears downstream of discharge. So this is one of the main phenomena and ideas that I would like to share in this lecture. So this VV pumping is a very interesting mechanism that we see in some systems. I like very much this nitrogen case. And it has been proposed that in CO2, we can have a similar pumping mechanism. And so we can take advantage of the vibration energy in the molecules to dissociate efficiently the molecule. So I will go back to this point just in a moment. But just to state there, then our goals in our research. So there are many teams around the world investigating this CO2 decomposition by plasma on Earth. And in this big context, we are trying to contribute to the definition of a reaction mechanism for CO2 plasmas. So I'm using the definition of reaction mechanism taken from combustion community, which is a set of reactions and rate coefficients validated against benchmark experiments. So this is our small role in this big effort in the plasma community to make an efficient dissociation of CO2 towards the production of fuels. So to this purpose, we are developing in Lisbon a detailed self-consistent model. And we have the experimental support from our colleagues in France and at the Netherlands. We are following a step-by-step validation strategy, meaning that we try to isolate specific aspects of the very complex chemistry, not only chemistry, physics as well, of these plasmas, and try to isolate different phenomena and validate in a unambiguous way, or as unambiguous as possible way, this reaction mechanism for specific conditions. And then, of course, hoping that in the end we can put everything together and gain a deeper understanding of the system and optimizing its operation and so on. So I will refer in the next slides two of these isolated aspects. One is this input and relaxation of vibration energy. So the first steps of the mechanism, so how the electrons are transferring their energy to the vibration states and how the collisions between vibration states, vibrationally excited states, start redistributing this vibration energy. So we are looking at the lower part of the vibration ladder. So of course, this is not what we need for the dissociation. It's the first step of this mechanism. And then I will also describe briefly what we have done regarding the electron impact dissociation of CO2, because in a plasma, although vibration energy is very important and we hope to use it in our favor, of course, electron impact dissociation is also extremely important. We are now moving to another isolated step, which is to validate the chemistry in vibrationally cold CO2. I will not describe this in detail because I will include part of this on the topic of bigger interest for you, which is then in situ resource utilization on Mars, where I will show what we have been doing in this regard. So let me just mention a bit what is the CO2 molecule so that we don't get lost in the next slide. So CO2 has 3 vibrational modes. So symmetric vibration, where we, the molecule just vibrates symmetrically with both atoms moving around the carbon, both oxygen atoms moving around the carbon atom. We have a bending vibration and we have asymmetric vibration. So we need at least 3 quantum numbers to characterize the degree of excitation of the molecule. So nu1 for the quantum of symmetric vibration, nu2 for bending, and nu3 for asymmetric. Then when the molecule is bended, it will rotate along the axis. And so we have another quantum number to characterize this rotation, which is this L number. We can have different mechanisms for this vibration energy transfer. So electrons can collide with a vibrationally excited molecule and change its internal state. We have vibration to translation energy exchanges we call VT, where vibrationally excited molecule collides with another molecule and it changes its internal state. And we have these vibration to vibration energy exchanges responsible for this pumping, where 2 vibrationally excited molecules collide and both change their internal state. We have a few selection rules. So this L quantum number for rotations can go on jumps of 2 quanta, finishing at 1 or 0 and starting at nu2, the quantum for the bending state. To make things more complicated, there is an accidental degeneracy and Fermi resonance, because 2 quanta of the bending mode are almost with the same energy of 1 quanta of the symmetric mode. So if we start with a molecule in this state and the symmetric mode decreases 1 quantum and asymmetric mode increases 2 quanta, we have nearly the same energy and the same symmetry for the molecule. So in fact, it's extremely difficult to distinguish these states, and they are always they always appear with a combination of the 2 states. So on our analysis, we define an effective level characterized by the 4 quantum numbers. So the 3 quantum for vibration and the L number. And then just to keep track of things, sometimes we had this ranking number to remind us how many states are in this effective level. So for instance, if we start with a 0, 5, small 5, 0 state, we denote it as 0, 5, 5, 0. And we can add 1 because there is only 1 level inside. But if we have the same quantum numbers for the vibration, so 0, 5, 0, but a different L number, 3 in this case, then we can increase 1 the symmetric and decrease 2 the bending, and we have 1, 3, 3, 0. And so we have these 2 grouped states, so 1, 3, 3, 0, and number 2, just to remind us, we have 2 levels. And the same, we can have L2 equal to 1, and then we have 3 states. And finally, so statistical weight is 1 for L2 0 and 2 for L bigger than 0. So just this slide could and should have appeared before if all these notations would be known to everybody. But it's just why this excitation of the vibrations is relevant in CO2. Because the vibrational excitation cross sections are very big. So they are represented here on red. And if we plot the fractional power transfer of the electrons in the different excitation channels as a function of the electric field in the discharge. So for typical discharge operation conditions, we have here these big curves, which are all excitation of the vibration states. So you can close a little bit the story that I was telling in the beginning. So in the gas discharge, it's very easy that when an electron collides with a CO2 molecule, it makes the molecule vibrate. We could see this is a drawback because we don't want vibration, we want dissociation. But in the end, if we find the conditions where this vibration up pumping is effective, then this is a good thing for us because we, at low energy, make the molecule vibrate and then step by step increase the amplitude of vibration until it will dissociate eventually. So now to the results of what we have done. regarding this first step, so this analysis of the input and the relaxation of vibrational energy. So we have a low excitation regime where we populate efficiently the lower vibration levels. So we don't have a very important role of high vibration levels, and we don't have dissociation. So again, this is not the conditions that we want in the end. It's to this purpose of establishing and understanding one specific aspect. So in this case, the first step of the mechanism. This is nice because we don't need to take into account, for instance, transfers between CO2 and CO or CO2 and O. It's enough CO2, CO2. And experimentally, this can be realized, for instance, in a DC pulse discharge at relatively low pressure. So we took 5 torr as our benchmarking conditions. We have other results at not very different conditions, but different conditions. Discharge current is 50 milliamps and the length of the pulse is 5 milliseconds. And our colleagues in France and the Netherlands developed technique with Fourier transform infrared spectroscopy, where they were able to measure the individual populations of molecules with quantum number nu1 up to 3, nu2 up to 6, and nu3 up to 5. So this was really a breakthrough that allowed a big development, both on the characterization, experimental characterization of the system, and then on the interpretation and on the modeling. So these conditions are very nice because this discharge is quite homogeneous and stable. So we can make a lot of different diagnostics, and we can also do interesting modeling on this. So we looked at the system and make then a validation of our system. So first in the afterglow, and then in the discharge. So in the afterglow, we try to validate that we don't have electrons, so we have only heavy particle collisions. So we try to validate our VT and VV rate coefficients. And then in the active discharge, we use the same VV and VT rate coefficients, and we try to validate the electron impact rate coefficients. So our model considers electron Boltzmann equation. So we calculate the electron energy distribution function. So how many electrons we have with each energy. We couple this to the rate balance equations describing the creation and loss of about 70 individual vibration levels. We have the rate balance equations for positive ions. We take the gas temperature from experiment and is given as input. We have an electric field, reduced electric field assumed constant in the pulse, and the electron density profile we estimate from the discharge current and the ionization rate coefficient. We can also calculate the gas temperature. We have in fact done so. But at this first step, if we have the value from experiment, there is no reason to calculate it. It could only propagate some error if we would not make a very accurate calculation. And we verified a posteriori that we can in fact calculate the gas temperature quite accurately. In the afterglow, we solve the same system of rate balance equations, but without electron impact mechanisms. We have our own code that we named Loki, that is developed in Lisbon. It is now a big improvement to our former codes, effort from our team led by Luís Lemos Alves, so it's the head of the team. And in fact, the Boltzmann solver is available. It's open source code in MATLAB, and it's available for download for someone who wants to calculate electron energy distribution function. Part of the difficulties were to choose the collisional data. So there are VT and VV rate coefficients for a few transitions. Okay, there are still a lot of transitions, but far from all the transitions that we need. So we take those essentially from this report from Blauer and Nickerson, and then we use the theories to scale from known rate coefficients to the unknown rate coefficients through different theories, SSH for Schwarzlowski-Hersfeld and Sharma-Brau, depending on the transitions. I will not enter on the details of these, but what is important is that these are first order perturbation theories, so they will fail when the transition probabilities will be very high. So we should keep an eye on the type of calculation we are making, have a warning bell if these probabilities became very high. And for electron impact rate coefficients, we have also difficulties because there is a limited number of cross sections. And they correspond to global energy losses at some energies, which are fine to calculate the electron energy distribution function accurately, but are not so fine if we then want to deconvolute these global losses into individual process. So we had also to think in this deconvolution process, how to generate cross sections for transitions that are not known, and so on and so forth. So in the end, we came up with about 250 direct reactions for electron impact mechanism, 450 for VT, and 800 for VV. Here you can see an example of a measurement. So you see here the gas temperature along the discharge pulse that is increasing, and then the pulse ends and it starts decreasing back to room temperature. Here in orange, you see the temperature of the symmetric and bending modes, which is the same, very nearly the same, and then decreasing again. And on blue, you see here the temperature of the asymmetric stretching mode, passing through this small maximum, stabilizing, and then going down. So one interesting thing in this figure is that you immediately see this non-equilibrium taking place. So we have a gas temperature here, we have a common vibration temperature for bending and symmetric mode, and we have a higher temperature for the asymmetric stretching mode, which is this mode where this VV up pumping may take place. So it took a long time to choose which reactions we were going to include, which rate coefficients we are going to include. And then when we made the first calculation, this is really the first calculation, it always surprises me a bit to look at this picture. We get the experimental data of the population of the first asymmetric level as a function of time in the afterglow. And we see here the measurements in black and the calculations in red. So the agreement is perfect. So of course we were very, very happy. And this agreement is extended to the populations of the other levels that were measured. So on the left, we see the populations of the first and second symmetric levels. So their population along the afterglow, and on the right, the populations of 4 levels of the bending mode. So the agreement is really excellent. And we can consider that we have a validation of our VT and VV rate coefficients and the reactions describing the kinetics of these states. So then it was time to move to the active discharge. So we keep the same set of heavy particle reactions and rate coefficients, and we add electron impact excitation. And you see here in red the model and in black the experiment. It's also quite nice. So we see a similar growth, this small maximum, and then some saturation. And again, this sort of behavior is also verified for the symmetric mode and the bending mode. So the agreement is not as perfect as for the afterglow. We have maybe here some room for improvement, but at least for now, we are quite happy with this. And we consider that we have also validated our electron impact set of reactions and rate coefficients. So the second isolated effect that I will tell you about, it's related to electron impact dissociation. As I said, we are in a plasma, so electrons will always dissociate directly for more that vibrations can be interesting. And here we found an unexpected difficulty because electron impact dissociation cross-section is still poorly known. So if we look in the literature, even in very recent papers from last year or 2 years ago, we see different authors using different cross-sections for electron impact. So I will not go much into detail. It's enough to look at the picture on the left-hand side depicting very many different cross-sections and to know that different authors use different cross-sections. And on the right-hand side, of course, we see the translation of the different cross-sections in a dissociation rate coefficient as a function of the electric field. And you see also difference of several orders of magnitude in these different rate coefficients. So we have many authors are using these cross-sections that produce this rate coefficient, and many others are using this blue, for instance. So you see quite different difference in orders of magnitude for these two mechanisms. Oh, sorry.
We have to assess this demonstration just because we need information. Can you?
Yes, I will move.
So, thanks. Sorry. Thanks a lot.
No problem. Okay, so sorry for this.
All good, all good. We still see you.
Yes. So, yeah, I will actually try to maybe see you as well, because it will not disturb and it will be nicer for me. Okay, good. So, okay, we have this problem that we don't know, this dissociation process. Section. So our colleague, it's again a DC discharge. So our colleague in a closed reactor, and it's a sequence of pulses in this closed reactor. So we have 3 times here. So it's the duration of the pulse, the time between pulses, and the total time before a measurement of the CO concentration is taken. And so the idea is that they don't excite vibrations, then the production of CO is only taking place by electron impact. And we can verify this with multiple combinations of these different times on the experiment and verifying that things do not change in a certain range. So if this is true, then the rate balance equation for CO is very simple. So the production is just electron impact colliding with the CO2 molecules times the rate coefficient. And this is what one figure that is from these results. It is not a best figure. So there are many, many measurements and they all show the same conclusion, which is if we change the duration of these times, of course, in the long times, we have different kinetics. So we see here that the saturation goes to different points. But in the beginning, when we are just starting to dissociate and there is no chemistry and nothing is taking place, all the curves overlap. So here we have a mirror really of this electron impact dissociation. So in this experiment, we can get the dissociation rate coefficient, which is plotted here in these black points. And you see that they almost perfectly overlap this yellow curve or black curve that goes here, which is the cross-section of Polak and Slovetsky. And so we think that we have now established what is the dissociation cross-section for CO2. We have a complementary confirmation on the right, where we have the calculation of the evolution of the CO concentration using Polak's cross-section, which is this red curve. Experiment is the black dots. And if we use one of the other cross-sections that is widely used in the literature, we are very off on this time dependence. So this was also a quite nice result that is now in preparation for publication. So all this is our research on Earth. So I'm sorry in a way that I drift from this more, let's say, fireworks type of presentation that we can do. But it's time then to return to Mars. So what about Mars? So pressure on Mars is 150 times lower than on Earth. And just to animate a bit, so how can the pressure help on this? I didn't mention any effect of pressure. I said that we took this range of pressures because this was nice to ignite the plasma and the discharge was homogeneous. But in abstract, if we want to ignite a plasma, do we need to have many molecules? Not so many molecules, somewhere in the middle, or it doesn't matter. So usually if I do a presentation for the students, I ask for a democratic votation. I will not really ask you to vote if you don't want, but you can at least think what you want.
Can I call a friend?
Yes. But okay, I will give you the answer because this is of course a quite abstract question, just to animate a bit presentation. So the answer is that we should be somewhere in the middle, because if we have very few molecules, it's very nice because the electric field will accelerate the electrons very fast, but they will not collide with any molecule. So this is not very helpful. And if we have a lot of molecules, then as soon as we start accelerating the electron, it will collide with the molecule. So it is still not enough energy to do anything interesting, it's already colliding. And then we try to accelerate again, but it's meeting another molecule. So it's nice to have low pressure. So this 5 torr that we used in the experiment is a nice pressure to ignite the plasma. And in reality, this is the pressure on Mars. So on Earth, very often plasma technology requires vacuum pumps so that we go to pressures that are more convenient. Or we use atmospheric pressure, not because it's the best for plasma, but because we don't want to increase the complexity or waste money with vacuum pumps. So on Mars, everything is ready from the point of view of pressure. And temperature is also lower than on Earth. So I can also make a very stupid question. So how can temperature help on Mars? Maybe it helps making the molecules sink, this vibration up pumping. Maybe it hinders back reactions, so not so much recombination of CO and oxygen back in CO2. Maybe it gives us time to separate products, or maybe everything together. You have 3 seconds just to think what you would vote, and everything, in fact. So if temperature is lower, all these VV up pumping is more favored, because the interaction between 2 vibrationally excited molecules on this VV exchange is dominated by long-range attractive forces. So if you decrease the temperature, these interactions become stronger, and so you enhance the rate of these reactions. And on the contrary, the VT reaction are just destroying vibration energy. They are dominated by short-range repulsive interactions. And so when we decrease the pressure, the temperature, they become less efficient. So both mechanisms, VV and VT, vary in different ways when we decrease the temperature, and in the good way for this VV up pumping. But it's also true that chemistry is slower, so the back reactions forming back CO2 take longer, and that gives us more time for separation. So these 2 were important points when we start thinking that plasmas could be interesting for Mars. And are at the essence of the presentation of the idea that we published in 2017. So we have 96% CO2 atmosphere where we have definitely oxygen. We have a low pressure, which is good for ignition of the plasma. We have low temperature, which is good for this vibration pumping and to slow down the chemistry. And we have traces of nitrogen and argon, which cannot be bad, because nitrogen is also known to vibrate a lot and to transfer its energy to CO2, like in lasers. And argon is atomic gas, so it does not have inelastic processes at low energies, And so the electrons can accelerate much easier when we have a bit of argon in the discharge. So we have more energetic electrons just because we have argon. So maybe nitrogen and argon will not make a big difference, but if they do make a difference, it will be in a good sense, not in a bad sense. So I used to joke with a religious expression of the type, God is all big wisdom has prepared Mars for plasma reforming. So all conditions are met. And so we had tried to verify these ideas. So we made the first calculation on that paper, and then we tried to verify these ideas, making a discharge in Martian conditions. So it was quite a challenge, but finally the reactor is immersed in a mixture of ethanol and dry ice around 200 Kelvin. So the gas temperature is around 220, 230 Kelvin. And the results, one first result is shown here. So the figure on the left is from our initial calculation, where we were reporting the ratio of the vibration temperature on the asymmetric mode to the gas temperature. So a characterization of this degree of non-equilibrium of the plasma on Earth and on Mars. And we see that it's higher on Mars than on Earth by about a factor of 1.6. So this was using the model that I have described before, just with these vibration energy exchanges. So in experiment, the absolute numbers are not the same, but are not extremely different. And we have a ratio of about 1.2 times higher, let's say, non-equilibrium on Mars compared to Earth. So this was a first good sign that, in fact, the Martian environment is favorable to establish this non-equilibrium that can help us make the molecules sink. So then we developed this next step, this model for vibration equal CO2. So we solved the electron kinetics in the actual mixture of CO2, CO02, and oxygen. We do the chemistry for all these species. We had a very well-established chemistry for oxygen with the ground state, metastables, atomic oxygen in ground state, metastables, ozone, and so on. And we add CO2, CO in ground and the metastable states, C2O, different ions. And then we close the system with electron and ion transport equations and the quasi-neutrality condition that allow us to determine self-consistently the sustaining electric field. So here we don't include vibrations, which we should do in the future, but also in these discharges that we are using, we don't expect the vibrations really to contribute significantly to dissociation. So we were using them to study vibration energy transfers, but they will not be really effective for dissociation. So this model should be quite okay. And the result is here. So you see here, as a function of pressure, the decomposition. So alpha is CO over CO plus CO2. So it's the degree of dissociation of CO2, which is nearly constant with pressure. It's increasing with the discharge current. It's fine. It's a mirror of electron impact mechanism. And the open dots are the experiments for Earth conditions and the closed dots experiments for Martian conditions. And the calculations, the curves, the corresponding calculations. So we see a small difference on the experiment that we don't capture very well on the modeling, but it's really small. I mean, all the trends and the orders of magnitude are perfectly fine. And so it's not a magic thing, like we go on Martian conditions and we dissociate immensely. But it's also not a bad news. It's that what we get on Earth, at least the same we can get on Mars. Using this discharge, which is probably not, or not probably, it's for sure not the best type of discharge that we should use for a real processing. This is, well, quite a busy picture. I don't want you really to follow it very well. It's just, okay, if you are then interested to see exactly how much O2 is produced and how much oxygen is producing, okay, this is according to the model, but we should not be very far off. So this is the steady state discharge, DC discharge. We have, okay, about 15% is on CO. Then we have 10% and a bit less, 7 on O2, and then we have on atomic oxygen. And so the last figure that I want to show you here is then the influence of the atmosphere in the sense comparing a discharge in pure CO2. So these results were all in pure CO2 with the actual Martian mixture. So CO2, argon, and nitrogen. And what we see, so sorry for these waving curves, we should have done maybe a different way. But what is interesting is to see that if the pure CO2 is the full lines and the argon, nitrogen, CO2 is the dotted lines. And so this influence of argon and nitrogen is actually helping on the dissociation, as it was a bit anticipated and discussed in this first paper. And you see this happening for different discharge currents. You can also see that for the lower pressures, this has a different behavior, which is probably linked to different mechanisms taking place on the surface. So it's other physics that starts to play here. So this is more or less what I had to say. So just to finish, let me make first the bonus. We start thinking on oxygen production, but in reality, if we really think on exploring Mars, probably the fuel production is much more important. But it's the same. So if we decompose CO2 in CO and oxygen, this CO and oxygen can be used to produce propellants. So that's perfectly fine. And maybe in fact the direction to follow. And then there is a proposal that is going to fly and to be tested by NASA to produce oxygen using a completely different technology, so electrolysis. It's this MOXIE program that will, well, it's foreseen that it will produce about 10 grams of oxygen per hour at a power of 300 watts. So if we make the maths, this means that we spend 36 electron volts per produced molecule. So dissociation of CO2 is at 5.5 electron volt. Electrolysis operates at high temperature and high pressure. So this is not the ideal environment on Mars in this sense that, okay, I was saying plasma, on Earth sometimes we use vacuum pumps and on Mars is perfect. So electrolysis is the opposite. So we use it on Earth. There we have to start by increasing the pressure and the temperature. So of course, big advantage of this is that it exists as a technology and it's very robust. We don't expect big surprises. So we know it will work. If I want to put it a bit on the downsides, the energy efficiency is not very high. And we have to use scarce and expensive rare earth metals in this. So it's really, of course, I don't want to say anything bad because I really don't think that anything is bad. It's on the contrary, a very exciting program. And it builds on a very robust technology, which is a big advantage. Plasmas are much less developed. There are reported energy efficiencies, but not for the whole process and just for the CO2 decomposition of about 80% from former Soviet papers in the 80s. And recently, there have been results reporting energy efficiencies about 50% for CO2 decomposition. There is a good reference on this paper in Faraday's discussion. And as you know, I'm now visiting Trento and I just discovered the master thesis of a student where they reported 60% on and they are still confirming the results, but it's also a promising result here. And so just to conclude, let me first say okay, in Lisbon, we are following this step-by-step procedure to validate isolated subsets of a reaction mechanism for CO2 plasmas. So we developed this comprehensive self-consistent kinetic model, and then together with our colleagues in France and Netherlands, developing a series of dedicated experiments to this purpose. So experiments on plasma production of oxygen on Martian conditions were carried out for the first time. Well, I put here a question mark. It's because first time is a very dangerous expression to use. So to the best of my knowledge, these are the first experiments on really Martian conditions, and we have a very good agreement of these experiments with the model predictions. So we first proposed and then confirmed that Mars has excellent conditions for in-situ resource utilization by plasmas for production of CO and oxygen. So low pressure is ideal for plasma operation. Low temperature will enhance the degree of non-equilibrium that will ultimately favor dissociation. And argon and nitrogen will also increase the decomposition of CO2. So we can have positive impact both following the path of exploring the non-equilibrium and all this vibration excitation, and by following the path of promoting electron impact dissociation. So it's possible to find different configurations where we can favor one of the mechanisms or the other mechanism, or some sort of equilibrium between both mechanisms. And so I really believe that plasma technologies are competitive with solid oxide electrolysis cells, but of course much less developed at this stage. And that's it.
Thank you, Vasco. So we're a bit late on schedule, but I still like maybe to take a few minutes to see if we have questions.
Okay.
Yes.
Sorry.
In the room. Let's start in the room.
So from what I'm hearing, it's somewhere, the system, when it matures, is at least 3 and maybe many more times more efficient than solid oxide. Is that taking into account the energy for compression and heating of the catalyst?
So the question is how to compare the efficiency with the solid oxide electrolysis, right?
Yes.
So, okay, let me answer in first, well, how to say, a very pragmatic way. So plasma technologies on Earth are being pursued. So of course the community believes that it can reach similar energy efficiencies as electrolysis. If then okay, it's an if, but there is a big effort and many big institutes following this route, so at least there is hope to arrive there. If then we transpose all this to Mars, there are many arguments why solid oxide electrolysis will be a bit less efficient on Mars than on Earth, and plasma technology will be a bit more efficient on Mars than on Earth. So this is, let's say, a very pragmatic, non-technical answer to the question, is that if these technologies could be comparable on Earth, then they are certainly comparable on Mars with some plus on the plasma and some minus on the electrolysis when we go from Earth to Mars. So then I don't know exactly the numbers of MOXIE, so I just go to, well, to their papers and their web page and take this what they aim. So of course they have now to demonstrate what will happen. I believe that this is what they expect as a final result taking into account everything, so including all these compression steps and so on. I think that this is accounted for in their calculation. For the plasma, it's a bit difficult to estimate. There is a quite solid knowledge on this efficiency for the decomposition itself, but the separation technology is not developed. So, okay, it's under development, so it's difficult to say at this point how much we will spend on separation and how much the figures from the decomposition in the plasma will be produced by the subsequent step of separation. So this is difficult to estimate at this moment.
Okay, I have a question also. So the current setups that you use to do the measurements in the lab, like how big are these?
They are not very big. So the discharge is 60 centimeters long, something like that, and 1 centimeter radius. Then you need a generator, okay? So that's in fact the heavy part of it. But one device is really quite compact. It's not very heavy. It is only cheap material, so to say.
Yeah. Yeah.
And you can run it okay with 50, 80 watts. So
okay. Yeah, I'm asking because you know, there is the efficiency of the process, but there is also all the effort and money that needs to go into developing an actual instrument. And if there is a technology that's maybe just a bit less efficient, but that already is prepared to go to Mars, then you have to make a strong argument on the efficiency increase in order for, you know, agencies or whoever to actually, you know, put the money in the effort of miniaturizing it, preparing it. But if it's already small and not very power hungry, then you're already closer, I would say.
Yes, I also think these are interesting advantages. So,
well, another advantage is that in any system that uses high temperature and catalytic components are very vulnerable to degradation. And so maybe a big plus is the life cycle factors of plasma being more robust relative to catalysts.
Mm-hmm.
Yeah, so in fact, this is, I think that the lifetime here on a system like this would be really limited by the lifetime of the generator itself, of the power supply itself.
Okay.
But if power is produced independently from you, then the lifetime of
the device itself, it's not really a problem. If I want then to be completely honest, to increase even more the efficiency of this process, we can think on coupling with some catalysts. So we can use plasma catalysis to enhance even more. So it's not necessary, and it can be made some interplay of these things. Mm-hmm. But let's say if we have, let's put a number that is not very meaningful, but okay, let's imagine that we dissociate 45% of our CO2. Then with the catalyst, maybe we can increase this number to 60%. So then we have to decide if it is worth to do it on this, your remark on the lifetime or not. Because the plasma system itself, there is no issue with the lifetime.
Okay. Do we have, so we're a bit late, so I fear that there's not much more time for questions, but does anybody online have questions? We want to give them a chance to. 3, 2, 1. Okay. Well, Vasco, thank you very much for presenting to us today. This was very interesting.
Thank you very much
Yeah.
as well. Sorry for being late.
Great job. No, no problem. It
You
was,
will warn me. Huh?
I appreciated that you took the time to explain to us how this works, because it's not, you know, it's outside of our field. So.
Well, and it also sounds very promising. This is something that maybe ESA or NASA will want to pursue in the not so distant future.
Yeah, that'd be great. And of course, we are more than willing to collaborate with whoever finds this interesting and is willing to help us on this effort. We are also, of course, willing to help, because it's, as you see, it's for us, it's really a curiosity and enthusiasm driven work at the beginning. And then when you think on the potential impact is really exciting. So.
Okay. Thanks, Vasco.
Thank you as well. Thank you.
Have a good evening.
Yes.
Bye.
Bye.
Bye-bye.